So let's say I have a flat track and I have a spring compressed with a box sitting on it, and I'm holding the system, and then I'm going to let go and the spring is going to shove the box forward. Okay, so let's say that the spring has been compressed a distance of 0.05 meters or 5 centimeters, and let's say that the spring constant is 10 newtons per meter, and the box has a mass of 1 kilogram. Okay, what I want to know is this, and again we're going to ignore friction. If I let this system go, what is the speed that the box will have at the end, or once it's launched? What is the launch speed of the box going to be? Well, when I'm holding the system before launch, then all it has is the potential energy of the spring, and then when I let it go and it launches the spring, once the spring reaches its equilibrium position, it no longer has any potential energy, and the box will be then shoved forward with its maximum launch velocity. So at that point, it will only have kinetic energy. So I can set this problem up as my initial potential energy is going to equal my final kinetic, which is what we've seen before, and that is going to be 1/2 kx squared is equal to the 1/2 mv squared. So I want to know what the launch velocity v is, okay? And now this time your masses aren't going to cancel out, okay? Your masses aren't going to cancel out. And that makes sense because a more massive mass is not going to be able to be shoved as quickly as a smaller mass. So any given spring with any given spring constant and the same compression is not going to launch a more massive object as fast as it is going to launch a very small object, all right? So in this case, your mass actually doesn't cancel out, but your 1/2s do, and so then I'm going to get that v squared is equal to k over m times x squared, okay? K over m times x squared. And if I take the square root of both sides, then we typically write this as x times the square root of k over m. And so this is going to be 0.05 meters times the square root of 10 newtons per meter over 1 kilogram. And notice, okay, what units am I going to get in here? So newtons are kilograms times meters per second squared. Divided by meters gives me kilograms per second squared. Divided by kilograms gives me per second squared. When I take the square root, I'm going to get per second. And when I multiply per seconds by meters, I get meters per second. So my units are indeed that of velocity. So 10 divided by 1 is 10. The square root of 10 is 3 and some change. 3 and some change multiplied by 0.05 is going to be approximately 0.16 meters per second, okay? Or 16 centimeters per second. So there's a few examples using the energy conservation or the conservation of energy, okay? So I hope you found those helpful. In the next video, we will explore friction and how to incorporate it into mechanical energy. We'll see you then.